any question from the last time? So this is going to be an overview. I'm not going into the details of any particular topic. Each of these topics would constitute 1 or 2 lectures in a regular course, okay? But I don't have the time. So I have to give you an overview of at least our galaxy in 2 lectures. That's a tough call. So anyway, so we talked about how people realized that we are not in the center of our Milky Way, right? That how far it is and what is the right, and then what is the motion of the sun and the nearby stars, right? And also the rotation curve, right? And then we realized that this is very different. And from the rotation curve in the solar system, yes.
How was the A and B coefficients measured?
Yeah, that is, so that will take a bit of time. But you can look it up. In fact, there is a Wikipedia page on Wood's constants. And that has some derivations also. If you are interested, you can look it up. So there will be a lot of things that I'll just probably mention and try to get the concepts so that you can go on according to your wishes and according to your curiosities. There are many resource books. So what does this imply? We also talked about briefly. It's also, we can do much more rigorous thing. For example, you can actually take the distribution of light in the Milky Way and then say that light traces the stellar mass, some sort of a light to mass ratio, which we know from stellar evolution, stellar structure, okay? Then you can say that, okay, this is the mass distribution that I expect from the stars, and that it does not really explain the rotation curve in totality. So you need something else, and that's dark matter. We'll leave this at this point. So radio, we were talking about radio waves, and that how in the visible wavelength light is not really good for probing the galaxy, the large-scale structure of galaxy, but radio waves can. And this is one of the early maps from the radio of the stellar spiral structure. So that is how we got to know that there is a spiral structure similar to what people have seen in other galaxies. In other galaxies is very clear, you see the spiral structure. But this was, some of these distance measurements are not sort of very certain, accurate. So now, of course, as I mentioned, that there is a satellite called Gaia, which has been able to measure the distances to a large distance. Large distance basically mean, this is the sun, and this is quite large, in galactic scale. And they have actually now, it has been superposed on a sort of a schematic diagram that is that conforms to what we know about the stellar spiral structure of our galaxy as much as possible. Okay, so this is not what our galaxy looks like, but this is a schematic diagram. What we know is a visual representation, and superposed on this, what they have done here is, this is from this paper. Red spots indicate objects with high metallicity. Metallicity, astronomers call all the other heavy elements apart from hydrogen and helium metals. Okay, that's all metals for us. Okay, because they are basically produced in the cores of the stars. So high metallicity basically means these are young stars, which means, see, as stellar evolution progresses, supernova you have heard of, right? It basically gives all the stellar yields inside the stars into space, and then a next generation star will form out of this nebula, which are already enriched in this heavy metal. So later and later generations are more and more metal rich, high metallicity. So they are young stars. Old stars are low in metallicity. So they are indicated in blue. What they have done is that you see that the red stars, which is the young stars, the high metallicity stars, later generation stars, yes?
So would that mean that young stars have, the core of the young stars would be already like carbon,
No, not enriched. Enriched means like by a little amount. Okay, okay. So these, they delineate the spiral arm. So this is what I want you to know, that young stars basically form along the spiral arms. That's what is to be noted here. And it is now known from Gaia observations. This is very, very recent. Okay? Now, why is that? And the idea is that spiral structure, the spiral arms, are not like blades of a fan, are not solid bodies that they are rotating like this. They're not solid structures. And there are problems if you think of this solid structure. They would have wound up and things like that. Okay, yeah. So the understanding that we have now of the spiral arms is like that. It's basically traffic jam in space. What is happening is that stars have their own orbits. They're going around like cars in a highway. Okay, but occasionally there are places where there is a sort of the density of cars is slightly large, because maybe there's a slow moving truck here, and behind that cars pile up. But it's not that this car is already always fixed here. It's trying to overtake, but it's going to take a time. Okay, so but if you look at from above, you will see that there is a high density region which is also moving. But this high density region is moving slower than the individual cars. Individual cars are piling up, slightly slowing down and then passing away. Slightly slowing down and passing away. But this pattern is also moving, but moving with a different speed. And that pattern is what we see as spiral arms. So spiral arms is basically, it's like a traffic jam. It's a sort of a pattern that we see. Now, okay, so this is another way of looking at it. So this is M51. There's another famous galaxy that we see face on, Whirlpool galaxy. So the stellar orbits are like this. Okay.
So, what is wanting to move out?
What is what?
Like you said that in traffic jam, usually cars want to move along. So, what is trying to move out of the spiral?
I am not coming to this. Wait.
Oh, sorry.
Okay. So what is happening here? So there are some certain region where, so for example, stars here, they linger within the spiral arm. So there's this certain sort of a high density region. So stars, when they slow down, they basically increase their gravitational pull, and the gas clouds, because of this gravitational pull, get compressed and form stars. Okay? The stars are going around in this orbit, but occasionally they will be sort of slowed down in this pattern. Okay? And whenever they do, the gravitational field will be stronger, and the gas which is also going with this, stuck in this, or in that region at that moment, will get compressed and form stars. So which makes sense that the stars form along the spiral arms, young stars. So you're likely to see young stars in. And young stars, as you have now understood from stellar evolution, young stars are most likely to be massive stars, because massive stars don't live long. So whenever you see a young star, that's likely to be massive. Okay, and the massive stars are hot stars, and so they have more UV radiation. So when you see a picture of this galaxy in UV, for example, you will see the spiral arms, like pearls. So the young stars basically, so that's the idea, okay? Now, right, young stars form along spiral arms. Now this is another view of, so let's go on to the, so spiral, how do you actually, how are the spiral arms actually created? That's another topic. This is the topic of the dynamics and the ideas of density wave, whether it can sustain itself once you excite it with some perturbation, okay? So that's a topic of, that's a very interesting topic, and one can just go on.
Sir, is there no end to that process? That means you were telling that new stars are getting formed once, like in that traffic jam.
Yeah.
Is there no end to that process, or is that process?
So that's what I'm saying. If it is it self-sustaining or not? Yeah. Okay, that's the question what one can ask. So I'm not an expert in dynamics, galactic dynamics, but this is a topic that people have been working on for a long time. So the idea that I have now is to give you a sort of a very brief guided tour, okay, to different places. Depending on where you, so suppose you go to Taj Mahal, right? You don't know where to start, where to begin. So you take a guide, and then guide will have, oh sir, half an hour only, 1 hour only, and just go to this place, this place, this place, this place. After that, you go around on your own, depending on where you think, oh, this actually looked nice, so I'll spend some time here. So my job is to take you on a brief overview of our galaxy, okay? Different aspects, different topics. So this is an infrared view. So infrared is like radio again, okay? It's not blocked by the gas and the dust. And so, so these are basically a few micron, and that's basically delineating either the old stars, cool stars, and also dust. Dust is heated up by photoelectric effect in the vicinity of massive stars. Again, UV photons, basically photoelectric effect, and then it basically heats up, okay? And then the dust then re-radiates in the infrared, okay, depending on its temperature. But from here we can see so since we are at this sort of the outer edge of the galactic disk, what we see is like what would have been seen by other galaxies also, because we are almost in the outer edge. Okay, so this is, you can see, you can take it as the view of our galaxy from another point of view. Okay, we're fair, I mean, practically speaking, very outside. So this is large Magellanic Cloud, small Magellanic Cloud, by the way. Okay, these are two satellites. And that's again another interesting point. How are the satellites, how the dynamics of the satellites in the gravitational field of our galaxy? Okay, that's another topic in itself. Okay, and if you look at, so this is what infrared view, visible also will be similar. But if you look at in gas, for example, H1, you will see that there is a stream here. So as the satellite galaxies are also rotating, so orbit, they have orbits, and as they orbit, they leave in their wake some gas, and that gas can be seen. Okay, and you can study that, and that actually delineates the orbits then. Okay, fine. So, but this is a sort of a picture then one can gather of our galaxy, that it has a spiral a structure, and globular clusters are here, and there is a bulge here, which is very prominent for it. There is a bulge in the central region of the order of a kiloparsec or so. Okay, and so this is the bulge, and of course the galactic disk. I will not go into the how there is a thin disk and there is a thick disk also. Different populations of different stars, okay, basically are located in the thin disk and thick disk.
So will the disk
Flip? Why?
rotation like sees
No, this is angular momentum. How angular momentum has to be conserved? How can you just flip? Okay, and in fact, the disk is there because of angular momentum. I'm sure you know that, right? And if you look at the orbits are like this. For example, the disk stars, as I said, they go around the disk, but they also have a vertical oscillation. Okay, and the vertical oscillation, as I said yesterday, the extent of the amplitude of the vertical oscillation will be determined by the mass density of the disk, which is mostly, there is not much of dark matter in the disk, there's mostly stellar material. So from the vertical oscillation, you can actually figure out what is the mass density of the disk. Right? So that's the yellow orbits here. Halo orbits, these are like the, for example, there are stars in the halo also. Okay, so this is halo, what we call halo, and the dark matter halo is really big. This is 10 kiloparsec. Say this is about 8.5 kiloparsec is the distance of the sun from the center. So suppose we say after 10 kiloparsec or so, the stellar density is very, very low. Practically that's the, you can take it as a size of the disk. If this is 10 kiloparsec, the halo where the dark matter resides is about 250 kiloparsecs. How do you know that? That's from, let me see if I can get there, okay? That's from what we understand from cosmological context of how galaxies form in the context of an expanding universe. Okay, I don't know whether I will get there at all. And then, so this is an idea of the, and this is about 1 kiloparsec. Okay, so there are stars in the halo, globular clusters. Okay, they are basically halo. So which is why their center of mass corresponds to the center of the Milky Way. And these are, so they're more spherical. The orbits are like this, spherical. Whereas disk stars are like this along the disk. Okay, and these are bulge stars. These bulge stars are mostly red stars, old stars. Okay, why that is so? Again, that's something that people are trying to understand. What is the formation of a process of bulge? Does the bulge form at the same time as the halo or the disk, or there's a co-evolution, or does the bulge form first and disk form first? One doesn't really know yet. Okay, so these are topics of basically that people pursue. Okay, all right. So this is a sort of a multi-wavelength view of our galaxy. As it's been clear now that the visible wavelength is not enough. Okay, you need to take the help of other wavelengths. So let's see very quickly. So this is the visible, this is the optical. This is what we'd have seen. You see the black patches here, dark patches? It's actually clear when you see, if you go to a mountain top and see the Milky Way, you'll see some dark patches. And these are basically either molecular clouds. Molecular clouds are thick, dense. Dense means what? Density is of the order of 10 to the power 5 or 6 atoms or molecules per cc. So one molecule, that's very, very small compared to the terrestrial density, right? What is the terrestrial density? What's the number of molecules? It's the Avogadro's number per 22.4, right? 1 mole. Right, so if you take a cc, a cubic centimeter, you'll get about 10 to the power 19 molecules in the air. Compared to that, molecular cloud is 10 to the power 5 or 10 to the power 6. But even that is large compared to the average density of the interstellar gas, which is about 1 atom per cc. Okay, all right. So these dark patches, as you would see, if you look at it in infrared, these dark patches become light because there's dust there. And the dust is, in the infrared, you can see the dust, the radiation from the dust, which is about temperatures of 100 degrees or so. So these dark patches become bright here, and different infrared, so infrared, mid-infrared, near-infrared. These are basically dust, I'm sorry. Near-infrared was just about 2 microns or so. You also can see molecular hydrogen, you can see molecular lines. These are radio lines, okay, from mostly carbon monoxide. Okay, that's a good tracer, and that's a very strong line. Then what I would like you to look at, this is atomic hydrogen from 21 centimeter, atomic hydrogen. So by looking at all this, we know the idea is to combine all these ideas and the information to build up a picture, a sort of a holistic picture of Milky Way, and to understand the dynamic. At that time, when this poster was made, the ultraviolet, there was no good survey, most likely.
Is there any reason for not having ultraviolet, or is
Now, ultraviolet is actually very difficult. So, okay, yeah.
The last slide,
Yeah.
you showed like there are oscillations of stars in perpendicular to the galactic.
Yeah.
But the baryonic matter is on the disk.
Yeah.
The dark matter is in a halo, right?
Yeah.
So gravitationally, a star like which is above the disk
Yeah.
would experience a force like this, not
Yeah.
this. So
What?
would experience like
No, it depends on the distribution of dark matter. The dark matter is not just some object here.
no, like it's in a halo, right?
Yeah, so it's in a halo, so it's everywhere, right? So if you look at the gravitational acceleration due to dark matter, it will not point to just one direction, no.
The net force.
So suppose there is a net force, I mean, I'm surrounded by dark matter.
So you are saying like the amount of dark matter like attracting me here is the same as the amount of dark matter.
It will depend on the gradient of dark matter.
Yeah.
So that the gradient is not very large here. So you have to, it's not just the presence of dark matter, but the gradient.
So the main force here is from the baryonic matter itself.
Yes.
Sir, dark matter is very constant.
We haven't come to that yet.
No, but yesterday there was a graph showing the dark matter distribution from the center to the edge of.
When you say distribution, what do you mean by that? Is it the density or what? So density, no, it's not definitely concentrated with the, it's concentrated near the disk. The density goes down. So you have to actually look at the plot, what actually the plot says, not just get an impression. Okay? In order to think logically, you need to understand what that plot is. Okay? And just the word distribution is a very vague word. What is it exactly you should, that if you look at the density of dark matter as a function of radius, it of course goes down. Okay, right. So there are also gamma rays, which I hope, let me see whether I'll have it in time, to what do they actually signify. There is radio continuum. It's about a few hundred, so radio continuum at a few hundred megahertz, high frequency. So radio continuum here basically is emitted by energetic electrons gyrating in magnetic fields. This is synchronous radiation. Okay, so that also tells us about where are these energetic electrons being produced and where the magnetic fields are, etc., etc. Okay, so different emission mechanisms are behind are the reasons for emitting at different wavelengths. And you look at the spectrum, etc., and you find out what is the emission mechanism, and so what is the source of this, and then you build up a picture. Let me then try to talk about the interstellar medium. Okay, what is there between stars? So it's been very clear from the very beginning that, well, the question was there whether this space is empty or not between the stars. You of course see that there are some dark patches that I mentioned, these sort of black clouds, and in about 1930, so this was a very interesting observation that Trumpler made. It's very easy to understand. He took a collection of sample of star clusters, okay, and bright star clusters, which had this similar luminosity, okay, and then what he so if you take the luminosity is 4 pi d square. So I can, if I know the luminosity, so in the sample that he had, all the star clusters more or less had this similar luminosity. Okay. Now I know the flux, I know the luminosity, so I can ascribe a density, a distance that I have inferred from the luminosity. So I'll call it dl. Okay. So this is dl is defined this way. I can also figure out its distance from its size, angular size, right? Because the star cluster is not a point object, it has an extent. So a star cluster, which is the same luminosity and the same size, by the way, basically it's a homogeneous sample. If I put the star cluster farther and farther away, it will look smaller, it will have a smaller angular size. So from the angular size, right, I know its actual size and I know its observed angle, that it's then I can then define a distance according to its size, its angular. So I have two modes of determining its distance. Let's look at, suppose, I mean, inverse square law holds and it's vacuum, then these two methods of determining the distance should be the same, should give me the same answer. Or if I were to plot dl versus dA, these two distances, I should just get a straight line, right? But I didn't get a straight line. So look at this data. It deviates from straight line. At what? At large distances, the diameter, the angular, the luminosity distance, this is the luminosity distance, is systematically larger. At large distances, the luminosity distance that you infer from luminosity is systematically larger. What does that mean? If this is larger than this, which means your flux is smaller than it should be, which means what? It's something that is in the intervening medium absorbing and making the flux dim, making them dimmer. Very simple argument. If you look at, for example, go to a straight road and you look at the lampposts. On a clear night, you can also do the same experiment. The lampposts all have the same size. Street lamps all have the same wattage. You can do the same experiment here. Okay, as you look at the farther and farther lampposts, they will look smaller and they'll look dimmer. And if you look at the two distances, they should have a straight line. But if you look on a foggy night, you will get a similar deviation from the straight line, right? So he inferred that there is something there which is intervening. So it's not empty, okay? And that's right. And then let's look at this infrared picture of the same dark cloud that I'd shown in visible light. In infrared light, you can actually see that there are, you can see the background stars, the stars behind it, but they're redder. Okay, it will remind you of why the sun looks red during sunset, because it has to, the sun rays have to come, pass through larger distances of the atmosphere, etc., etc. And so people have looked at, so there is dust there, okay? And you can actually, since we know what kind of stars they are, by looking at the spectrum, I can figure out, assuming that they are main sequence stars, I can figure out what their temperature is, what their luminosity is, and I know what I am getting, the flux that I am receiving, so I can find out how much of light has been attenuated, the extinction, sort of. And I can then plot the extinction as a function of wavelength. And that is very different from 1 over lambda to the power 4 that you expect from Rayleigh scattering. Okay, Rayleigh scattering, you should expect that, you know, it should be 1 over lambda to the power 4.
Extinction is that absorption?
No, extinction, it's both absorption and scattering. So mostly scattering. So, okay, so extinction means both. Something is basically taken out of my line of sight. Okay, and so you infer the presence of dust scattering. So it's not Rayleigh scattering, but it's something called Mie scattering. Okay, okay. So that's again a topic that one can spend, you know, lectures on. So how we infer not only the presence of dust, but we can figure out the sizes of these dust grains, and because just looking at this and studying this, and then not only that there is the slope there, but you also see some spikes. The spikes actually correspond to some particular bonds, like silicate bonds, graphite bonds, which make them absorb more in certain wavelengths. Okay, and that you infer the composition of the dust also. So we know that, you know, dust particles are mostly graphites and silicates of different types, and also infer the sizes, the distribution of sizes. This is how, by the way, C60 was, the presence of C60 was first inferred. Harry Kroto was an astronomer who got the Nobel Prize, by the way. Much before the chemists synthesized C60 in the lab, he had, from studying the interstellar medium, inferred the presence of C60, okay? And so he was also given the Nobel Prize. So studying the interstellar matter is important in for many reasons, and this is one of them. All right. One can go on talking about dust. Dust is very important. I hope I'll have the time to talk about some other aspects of dust. But okay, these are another very interesting parts of our galaxy where you see the nebula, gaseous regions which are illuminated, and these are basically ionized gas around massive stars. Okay, and massive stars, basically stars are not born in an isolated fashion. They are born in clusters. Okay. So when you see massive stars, you see massive star cluster, and the gas around them, and so and massive stars are hot stars, and they have a lot of UV photons, and the UV photons basically ionize the gas around them, and these are we call ionized or H2 regions. H1 is neutral hydrogen, H2 is singly ionized hydrogen, which is ionized hydrogen, and these are great objects to study. You see the red light, red color? Can you guess where that color comes from? Infrared. This is, by the way, this is visible wavelength photograph. Okay, it's okay. Any idea? No. Where is the red light? What is the wavelength of this red light? This is basically the Balmer line. Yeah, 322 line. Okay, 656 or something nanometer. Okay, so that's Balmer line, and there's a reason why it is so prominent. If you look at all the nebula, if you look at Orion Nebula picture, the red color is going to be very prominent. There are other colors also. So okay, you must have seen this picture, like pillars of creation or whatever they call. And there's a lot of things happening here. Okay, these are basically part of molecular cloud, big molecular cloud, where stars form. And when the stars form, and basically the emergent ultraviolet photons, they ionize. First of all, they destroy the molecule into neutral atom. Then the neutral atom is ionized. So, and then also there's some shock compressing of the molecular gas, which then forms another set of stars. A lot of things happening here. There's a like ionization front. So there's a front moves. It's ionizing photons keep ionizing. So one can look at the structure of this. Suppose I think of a very simple schematic diagram of a spherical region of ionized gas. There is a massive star here, and the source of the ionizing photons. Here we have neutral hydrogen, suppose, and here is a spherical region of H2 region. If you look at the processes, what's happening here, gas is ionized by the UV photons of the massive stars, and they have high surface temperature. But ions also keep recombining with elements, the electrons. So that's two processes going on, ionization and recombination. It's ionized, right? The photoelectron then photoionizes the atom, but then you have a proton and electron. Suppose it's only hydrogen, for simplicity. Then you have proton, electron. They will also recombine. There are two processes going on. And it turns out that there is an ionization equilibrium in the sense that there is a balance between ionization and recombination. There's also a thermal equilibrium because of photoionization, the photoelectric electron, the ejected electron has a lot of energy, and it shares because of collisions, it shares its energies with ions and electrons, and then basically heats it up. Okay, heats up the gas, but there's also cools. Cools how? We'll talk about this. So heating by UV photons and cooling by basically line transitions. So when you have recombination, so say proton and then electron recombines at a very high Rydberg level, but then it cascades down, right? And they all basically radiatively jumps to lower and lower levels, and the photons go out. If it is optically thin, if it is optically thick, then something else. But these are optically thin material. So photons can go out, then it can cool. So collisions due to random thermal motion, it excites the electrons to higher level, and then the electron then jumps to a lower level and then radiates the photon. So ultimately, you take the energy of the random motion, kinetic energy of the particles, which is the temperature, into photons, and which is given out. So ultimately, the temperature drops. So there is a cooling, there is a heating. And it turns out that there is a sort of a balance. And the balance gives a temperature of about 10,000 degrees. So all these photoionized gas around massive stars are typically at 10,000 degrees. Okay, now it requires a lot of calculations. I'm jumping over all these calculations. I'm just giving you the basic idea of what are the processes involved and what is it that we know. Okay, okay, right. So for example, this red color. What happens, as I said, the cascades down, right? So 322, you would say, why not 221? What happens is 221, the Lyman alpha transition, that photon gets absorbed immediately locally. Okay, because the Lyman alpha, the transition strength, the cross-section for absorption is very, very large. Okay, so it gets absorbed locally. Only the 322 line gets out and hits our eye or camera. So which is why red color. So this is the 322 line, right? This is the Balmer series. There are also some transitions which are sort of forbidden in the when we talk about quantum mechanics, because it's not forbidden, it's basically low probability of transition. So what happens in a terrestrial laboratory, suppose I have two states, and suppose the electron, this transition rate is that of a very low probability, which means transition rate is very low, which means what? The electron lifetime is very long. Electron stays in the upper level for a longer time because the transition probability is low. In terrestrial conditions, what happens? The electron is knocked down by collisions. Before it can jump radiatively, it is collisionally de-excited. Okay? But in space, the density is so low that the electron can go on residing for a long time and it radiates. So it actually, you see the photons which you won't see in terrestrial laboratories. So these are forbidden lines. So there's, for example, green light, there's O3 line. So for low density in ISM allows the electron to make the radiative transition before it gets collisionally knocked down. Okay. In fact, so this is a spectrum that was taken in 1864. By the way, this is 5 years after Kirchhoff and Bunsen wrote that paper on spectroscopy to understand spectral lines. And this is 5 years after that. And they saw in this planetary nebula, Cat's Eye, also called Draconis, a line, two lines at 4959 angstrom and 5007 angstrom. Here are the two lines. They thought, I mean, he and his wife, there were a team, they thought it's a new element because at that time, you see, new elements were being thought about. Helium had been sort of been talked about, not quite discovered in the laboratory. So people, whenever they saw a line that didn't match any terrestrial laboratory lines, okay, they thought it's a different way. So they gave the nebulium. But later on, of course, after understanding the advent of quantum mechanics, we could realize that this is because of doubly ionized oxygen. There's a transition. And it won't be seen here on Earth, but it will be seen in space. So that's cool. You know, just by looking at, and these lines, looking at these lines, studying these lines, also then tell us what the density of this gas is. Because if the density is very high, you won't see these lines. So there is some critical density associated with every line, every such forbidden line. And there are many such forbidden lines. This is one prominent, and that's in green. So some of the green colors that you would see in nebula, that comes from this doubly ionized oxygen. So a lot of interesting microprocesses at work, which is another reason why, you know, astronomy, I think is a very nice way of, interesting way of learning physics, you know. So in normal quantum mechanics, you won't get this. All right, so then there is cold H1 gas. And how cold is this? This is typically of the order of, this is diffuse H1 gas. Diffuse means not particularly near any star cluster or star, but distributed throughout the galaxy. It's of the order of 100 degrees Kelvin or so. And you would say, why 100 degrees Kelvin? And there is also a quantum mechanical reason for that. And that's because of carbon. The abundance of carbon after hydrogen, helium, carbon, oxygen, they are basically very important. I mean, the next in line. And there is a fine structure line in carbon. You know, you understand fine structure line, right? I mean, that's a coupling degeneracy broken because of the spin and orbit, okay? And so there is a fine structure line at 158 micron of carbon-2. Carbon-2 means, C2 means singly ionized carbon, and that plays a very important role. And so whenever the energy, the temperature of the gas is larger than, so if 158 micron, right? If you convert this to frequency and h nu, and if you convert this to write kT, kB, Boltzmann constant times temperature, you will get a temperature of 100K. So that transition corresponds to a temperature of 100 Kelvin. In other words, if the gas temperature goes far below that, far above that, then basically it's cooled down by this radiation, which is why there's also some sort of a thermostat going on here in cool, cold H1 gas. And of course, the observations also show that, you know, whenever you see cold clouds, this is infrared, far infrared, you'll see a preponderance of this carbon-2 line. There's a spectrum on that. I have written an article in Resonance. I don't know how many of you read Resonance. Some time ago, you can probably look up where I have derived very simple manner from, it's not a quantum mechanical calculation, it's a semi-classical calculation that you can follow, why this 158 micron line is important. Okay? Resonance. Okay. Right. So now let's talk about supernova. That also heats the gas. So we have talked about different gas at different temperatures, right? Cold gas at 100 degrees, ionized gas near massive stars at 10,000 degrees, 10 to the power 4 gas. I'm talking about now, there is also gas at very, very high temperatures, million degrees, okay? And that comes about because of supernova shocks. The supernova going on all the time because of, if the stars are formed, they will also be supernova, because a fraction of these stars are going to be very massive, and which are at the end of their thermonuclear fuel, they will going to go supernova. Typical explosion energy is 10 to the power 51 ergs, and I think this is what Karthik wanted you to estimate yesterday, right?
I got a value around 10 to the power 7 meters.
10 to the power 7 meters, so that's, let's see. Yeah,
Kilometers.
yeah, typical,
So
exactly.
we don't need relativistic effects.
Relativistic effects are there, but no, not in this. Okay, an ejector mass is about a few solar mass. That of course depends on the mass of the progenitor. Okay, but typically, so as you say, this is very simple to just, you can figure out what is the typical speed of the ejector material is going to be, initially at least. Right? So it's a very fast, and it expands fast. So this is a picture of a supernova remnant in different wavelength. This is X-ray, visible, infrared. So visible is only this, and you would expect, why is there X-ray? X-ray, if you look at, just again, h nu, if you just equate this to kT, you'll get a temperature of million degrees or above. So you'll need a gas which is hot to about million degrees or above for it to emit X-rays. Simple argument, h nu if you just equate to kT. And what is this million degrees gas coming up from in here, for example? So people can study this, and this is very interesting similarity between what the dynamics of this, the mushroom cloud of the atomic explosions, and studying that actually gave a lot of inputs to studying of the supernova remnants also. Now, what are the important parameters here? The energy of the explosion. It was a point explosion. Okay, I mean, a large amount of energy was basically dumped at one point of space and time. And then you're going to look at how the effect basically propagates through space. And if you look at the parameters, important parameters in this question, is energy, how long after the explosion that you're looking at, and what is the ambient density. And so if these two, so if remember you have done dimensional analysis, right? If the radius depends on 3 parameters, you can figure out how it should depend. Or in other words, these 3 parameters can be combined in only one way to give you radius, okay? And this is this. And so, so radius goes as T to the power 2/5, okay? Energy and density. And the story goes as both Sedov and Taylor. They were fluid dynamics experts, and then there's a story of Oppenheimer also, or maybe Taylor said of that, how did they estimate the bomb explosion energy by looking at, so they had either a leaf or sand, and they just let it go through, and then they realized what is the speed of, at that, they knew the distance, they knew R, they knew T, and they knew the speed, okay, and they knew the ambient gas air density. So you can figure out what the E is. That's how the energy of the atomic explosion was first estimated. I mean, these are anecdotes, but one can actually do that. But this is just, you can say that this is dimension analysis. How do you know that there is not a numerical factor here? There could be a numerical factor, but you can do a rigorous fluid dynamical analysis, and you can show that the numerical factor is close to 1. Okay, so the velocity goes down. Okay, so initially it starts with 10,000 kilometer per second, but initially the momentum is so large that it does not, the ambient gas does not affect, it just expands freely. So we call it free expansion phase. After a while, it is going to accumulate. It's going like a bulldozer. It's going to accumulate the material around it, and it's going to slow down after. Think about a bulldozer. Initially, if it's piling up things around it, mess around it, right, and it's going very fast. When is it going to slow down? It will slow down once the mass of the piled up matter becomes equivalent, comparable to the mass of the bulldozer itself. So when the swept up mass becomes equal to the ejecta mass, which is a few solar mass, it's going to slow down. Okay, and it actually you can show that it actually does that. So, but then this is how it goes. So this is the radius. This is the time. Initially, it expands very fast. It's like a free expansion phase. Then it slows down. This is the Sedov-Taylor phase I'm talking about. Okay.
Sir, I think it's analogous to fluid dynamics.
What? Say it again.
Fluid dynamics.
Of course.
Yeah.
It is fluid dynamics. Okay. So, I mean, these calculations have been done with fluid dynamics. Okay. So, and then you can at any moment you can figure out what the velocity is. So, velocity decreases, but velocity decreases from 10,000 kilometers, say, few hundred kilometers or so, and then it shocks a few hundred kilometers, even at the Sedov-Taylor phase. Okay, this is at the Sedov-Taylor phase now. So, at different phases, I've shown you representative pictures of different supernovae. This 1987A, you must have heard of it. This was in LMC. And it has just about finished its free expansion phase and gone into a Sedov-Taylor phase, by the way. Sedov-Taylor phase means this is slowed down a little bit. Okay? And I'm not going to talk about the radiative phase. What happens then, the piled up material becomes so dense that it's then it starts radiating. The radiation mechanisms are all two-body processes. You need two particles to radiate, say electron and proton. Okay, and the proton decelerates, then it emits radiation. Basically, it goes as n square. It scales as density square because it's a two-body process. So when the density is large, radiation can become very, very important. Radiation can lose lose energy. Now, so you can find out the velocity at each phase. 100 kilometer per second velocity, if it hits a gas whose acoustic speed, which depends on its temperature, it's say about 10 kilometer per second. So typical acoustic speed in the interstellar medium is of the order of 10 kilometer per second, the sound speed. And you hit it with something which is like 100 kilometer per second. It's like a supersonic motion. Okay, and it's going to heat it up. And you can actually show that from fluid dynamics again. So basically what happens, the bulk kinetic energy, a part of this is going to be converted into random thermal motion, which basically heat up the gas. So it heats up the gas. And that's how you can actually show that from fluid dynamics, that the temperature of the shock heated gas goes this way, scales as V square, the V of the shock of the gas. Okay, and there's a proton mass involved. And so, so this is how a 1,000,000 degree gas is produced, which shines in X-rays. Okay, so all these things are needed in order to explain all the multi-wavelength picture of the galaxy that we have seen. You've seen X-rays, infrared. So all these processes need to be taken into account. Yeah.
So this is what we call as thermal parameters.
No, this process of shining in X-ray, yes, thermal bremsstrahlung, yes, but this is shock heating. Okay, okay. So bremsstrahlung is basically breaking radiation. As I mentioned, if you have a total plasma, an electron passes by an ion and it decelerates, and deceleration is then going to produce it's going to emit photon. All right, so this is a picture of Vela supernova. So supernova remnant then keeps going. It keeps losing energy. At some point, it's going to lose energy by radiation, as I said, and then it's going to slow down, and then at some point, its speed will become comparable to the acoustic speed of the ambient medium, which is 10 km per second, 20 km per second, and then it's going to become a part of interstellar medium, just as Vela supernova remnant has become. Okay. This is very close to solar system, by the way. All right. So, so they become a part of this the interstellar medium. Okay. But by that time, this is enriched in heavy elements. They will produce a nebula and maybe a next generation stars. Okay, etc., etc. So this is sort of a synthetic picture, very simplified picture of gas in the interstellar medium, gas within our galaxies at different densities and different temperatures, and what are the processes that produces these gases at different temperatures. And then, so at very high temperature, for example, 10 million degrees or so. So there are wind-blown bubbles that I have not actually talked about, but I talked about supernova, very diffuse, but X-rays, and this is the typical temperatures. Then you have H2 regions, and I mentioned that the typical temperature is about 10,000 degrees of the photoionized gas H2 regions around the massive stars. Then there are regions which are between, see, this is this picture I had, very, very complicated things going on. So this molecular cloud, there's molecules there, and there's a massive star which has not only destroyed the molecules, but also into atoms, but also ionized the atoms. So there are intermediate regions where there is partially ionized, there's atoms, and so there's going to be transition from ionized gas to atoms to molecules. So all these intermediate regions are also there. Okay. So we call them photodissociation regions. So at various temperatures. Okay, and these are they have all of these ions, atoms, molecules, and then you have very dense and cool molecular gas. So temperature decreasing this way, density increasing this way. Okay. This is a sort of a very schematic table of the different phases of gas that one encounters in. So I think others, Professor Dwarkanath and Mosimi Das, they're all going to talk about in detail. So briefly then, we have molecular clouds. We know its temperature is roughly about 20 Kelvin or so. These are the densities, particles per meter cube, and this is molecular. Then there is cold neutral medium. Then there is warm neutral medium. This is H2 region. Even in the neutral medium, there are cold and slightly warm. Warm means a few thousand degrees. Okay. How do you know about all this? Looking at observations. Okay, you look at the H1 emission, for example. The width of the emission line is going to give you the temperature. Okay, so you know that. And in fact, RRI played a very important role in studying the warm neutral medium. So Professor Dwarkanath he was involved. So he may talk about it, among other things. And then so this is the H2 regions, typical temperatures 10,000 degrees. These are rough figures, by the way. Okay. Then there is hot ionized medium, shocked by supernovae. Okay, million degrees or above. Okay, ionized gas. So these are the gases, sort of the phases that we see. Phases not in the same manner of speaking in solid state physics. Okay, there's no phase transition here. Okay, these are just gas at different temperatures. Interestingly, if you look at the temperature and density, you'll notice something. You may have noticed it already. Just multiply them. You'll see that they are more or less at similar pressure, NKT. So there is some sort of a pressure equilibrium between all these gases, which is interesting. Okay. There is also something called, when you talk about components of the space between stars, apart from gas, there's also, I mentioned dust, there's also cosmic rays. Cosmic rays, as you know, they keep bombarding the Earth, and Victor has discovered this by going up in a balloon. And so this is sort of the energy distribution of cosmic ray particles. So number density of particles within a energy bin. Okay, so it's like a histogram of in their energy. So this is the energy in EV. This is sort of, it's also the flux, but you can convert into number density also. And you can see that there is a very interesting, there's a power law, very different from Maxwell-Boltzmann distribution, by the way. It's not thermal, so they have not been thermalized. Okay, and how do you produce them? There's been a question of how do you produce these cosmic rays and explain their energy distribution. Fermi had worked out, given a model in 1949. Now we sort of think that most of them come from supernova, accelerated by supernova. Yes.
So is that cosmic ray means any molecules or?
No, so these are basically electrons, ions, and different ions. Okay, and right. So these, as you can see, these are very, very high energy, 10 to the power 19 EV. Can you tell me how much in joule? 10 to the power 19 EV. 1 joule, right?
1.6 joule.
Roughly. Okay, 10 to the power 21 LB, say 10 to the power 20 EV. 10 joules?
Yeah, 60.
How much is a joule? Do you have an idea?
Very simple.
How much is a joule? How many joules did I expend here? It's about a few joules. Yeah. So just figure out, suppose I drop a Coca-Cola bottle something from the first floor, okay, and it falls on your head. You can figure out half mv square. You can figure out what the energy is, right? As it just hits the ground, it's going to be a few joules. Okay, so that amount of energy being carried by one particle. These are ultra relativistic, particles, ultra high energy particles, cosmic rays. How do you actually energize a particle to that much of energy? That kind of energy is it boggles the mind. But again, these are questions that people ask. But suppose we consider it's 12 o'clock. Can I take 5 minutes? Okay. So I'll skip here. Basically, one can actually connect these cosmic rays to supernova rate. And the supernova explosion and the shock wave, you can figure out, one can actually explain the acceleration of these particles in the shock waves. And connect the flux that we see in cosmic rays that we see now to the supernova rate. And I'll just flash this. How do you know the supernova rate? Is there another way of looking at, because we haven't seen supernova in our galaxy for a long time. Last one was Kepler. After that, we haven't seen any supernova, right? But whereas there is an element which is produced in supernova, aluminum-26, that's a radioactive element, and there is a half-life time of about 1 million years. So that can sort of infer the supernova rate in the last few million years. And aluminum-26 emits light in gamma rays, which can be seen. And this is, from there, we have seen, one can infer that there must be in our galaxy about 2 supernovae per century. Now you can ask, why haven't we seen a supernova in the last few centuries? Dust, gas. We can't see beyond a few kiloparsecs. So even if a supernova goes on the other side of Milky Way, you won't know.
So
Okay.
we can't see them using infrared.
Now, first of all, you have to see supernova just light up and then they just go. Transient objects, right? So anyway, so what I have tried to do here is to connect the energetics, but I'll skip this. Okay, So energy density of cosmic rays in the interstellar medium, I would like you to remember this. It's about 10 to the power 12, sorry, ergs per cc. So about 1 eV per cc. Okay. There's also magnetic field, and I told you that we see some of the radio continuum, a few hundred megahertz. If you look at the sky, that radiation comes from synchrotron radiation, which is basically electrons gyrating around magnetic fields, and you can actually, that is one way of inferring the presence of magnetic field. There's also Zeeman effect. There's also magnetic fields also polarizes because of dust grains. Starlight is polarized because of magnetic field, and basically from all this one can figure out that there are magnetic fields. And what is the typical energy density? It's a few, the field strength is about a few microgauss. And then the implication is that the energy density is of the order of, again, EV, half EV per cc. Okay? It turns out, if you look at the energy density of interstellar radiation from stars, starlight, it's also of the order of a similar, half a EV per cc. What's the kinetic energy of clouds? I told you the acoustic speed of 10 km per second of clouds, there are diffuse clouds. Typical energy density is again similar. So that's very interesting. There's a synergy between all these, there must be some synergy between all these processes, right? So one has to understand. So this is what one tries to understand in a galaxy in interstellar medium. Why is the, for example, a sort of a equipartition of energy between all these components, cosmic rays, starlight, magnetic field? There must be some sort of a very dynamic kind of interactions going on. Also, I mentioned that they are in a pressure equilibrium. That's also interesting. Why are they in pressure equilibrium yet on different temperatures? What keeps them in stable pressure equilibrium and at different temperatures? That's another way of a topic of study. Yeah, so ultimately I just stop here saying that, so ultimately there is a sort of cycle that you can think of. So there are molecular clouds which form stars, nuclear fusion in stars. Some gases return to the interstellar medium, which you can see during the supernova remnants, the hot bubbles, and then it becomes a part of the interstellar medium, becomes cold again, and part of the molecular. So that's a cycle. Okay, so this is a very simple overview of some of the processes that are going on at the interstellar medium that we know, some of the objects that we know, and what we think is happening there. I'm sure Professor Musimi Das and Professor Dwarkanath, they will say something more in detail. So I had in mind to talk about the galaxy formation, but there's no time. Okay? Any questions?
So, I had a question. So, when you talked about the supernova explosion, we can also associate gamma ray bursts along with it, right? Or because you talked about.
Yeah, a supernova of a particular of very massive stars may be related to gamma ray bursts.
So, does that cause any kind of differences compared to the other ones? Like, because they are much more energetic compared to.
Much more energetic, but they're very rare. Very massive, right? So if you look at the spectrum, the mass distribution of stars, so those stars are going to be very, very rare.
So what about hard Jupiters?
What do you mean by hot Jupiters? Brown dwarf.
Yeah, brown dwarf.
No, so I think Professor Srinivasan has talked about the limits, lower limit and upper limit of mass, right? So at if the core temperature is not enough to ignite thermonuclear reaction, for that you need a certain threshold temperature, right? So you need a certain mass, and which is why you have a lower limit to the mass of stars.
How can we detect? Is there
Infrared. So they're going to be hot, but not so hot.
So is there a way to how to detect
Infrared.
infrared? Okay.
Yeah.
Sir, in the interstellar medium, you talked about UV photons. So, where do the UV photons come in first place?
Because there are some stars which has a surface temperature of about 30,000, 40,000 degrees. O stars, B stars, okay, very massive stars. So very hot. Surface temperature is very hot. If you look at the black body radiation at 30,000 degrees, you will see there's a significant fraction of it is in the UV range. It's just that.
There can be a few material things like comets and
In the interstellar medium.
and interstellar medium. How do we define them?
I don't know whether there are comets in the interstellar medium. I mean, probably in around the inner planetary systems of different stars. But the gas that I'm talking about is a gas at large, not within any planetary system. Okay. All the best for the rest of your summer school. It's nice to teach. Stop. Switch off money. So all of you have had quantum mechanics or no? Quantum mechanics? Some of there's some MSc students here. Your batch, which year? Which year are you? Second year. You have not had the quantum mechanics yet. But you know, very basic ideas of Bohr model at least. Bohr model at least you have. So that's. But statistical thermodynamics. So that is at the heart of a lot of things in astro. But it's a fascinating subject anyway, statistical thermodynamics. It's one of the most beautiful subjects in physics.